If we can start, the excellencies of ICSMGE committee and all beloved audience here, good morning, ladies and gentlemen. In this special occasion, I proudly propose my paper with title is Deterministic Assessment and Numerical Simulation of Buckling Stability of Bell in Liquefiable Ground. Let's get down to the business. Before going to my presentation, I would like to explain my outline. There are 5 outlines as follows. The first, introduction, analysis methodologies, case study of buckling of pile, numerical simulation. The finally is conclusion. Last 2 decades, we know that there are several building and bridge severely damaged in the liquefied soil after a strong earthquake. During the Corbe earthquake of 1995, the building moved 2 meters and tilted off 3 degrees toward the seaside. In the figure, Soa Bridge fell during the 1964 Niigata earthquake. It had collapsed due to the buckling of pile foundation was caused by lateral splitting of ground. The main objective of present research can be summarized as follows: to review the current understanding of geotechnical engineering problem due to the soil liquefaction, to determine various influence including the axial load, ground inclination, pile spacing, and diameter on the pile and soil in the liquefiable ground by using deterministic and numerical simulation approach, to improve the understanding of pile-soil interaction during the earthquake liquefaction through numerical simulation, finally, to justify the capability on the numerical simulation on buckling of pile in liquefiable ground. The initial state, the force and deformation behavior of structural pile during the earthquake shaking are shown in the slide. Case 1, the axial load on the pile in the normal condition. Case 2, the earthquake shaking, the external pressure will build up, the soil started to liquefy. Case 3, the pile began to lose its self-resistance. Case 4, ground movement caused kinematic load on the pile foundation. An analysis flowchart in the method is shown in the slide. The method provides straightforward to integrate geotechnical assessment. Liquefaction analysis is based on the SPT and value. The right side, the parameter needed to calculate the critical length of pile, namely HC. We can say the HC is capacity and DL is acting force. The DL is the unsupported length of pile. The buckling of pile is safe when the buckling index is greater than 1. Then the pile is considered safe. Otherwise, the pile will be buckling. In order to compute the critical length of pile, HC, and buckling index IP, we should follow subsequent calculation: acting moment, the additional dynamic load of inner and peripheral, the dynamic axial load, critical length of pile. Finally, we can compute the buckling index. If we compute in buckling index is greater than 1, the pile is considered safe. Otherwise, the pile will be buckling due to the seismic loading and soil liquefaction. The case study is related to construction of coal-fired power station in Central Java with capacity 2 times 1,000 megawatt. The study area reported that Pati earthquake of 1990 with magnitude of 6.8 was occurred at the distance of 45 to 50 kilometers away from the project site. The study area covered 3 main facilities, including the boiler 5 and 6 and CCP. The foundation for soil unit 5 and 6 are supported 1300, 1300, and 232 precast concrete pile respectively. In order to evaluate the pile buckling, we select 47 representative pile, where 16 pile for unit 5 and 6 each and 15 pile for CCP. A total 16 borehole logs spread out in the study area. We adopt PGA 0.21, a magnitude 6.8 based on the historical seismic in the study area. Also, the energy Raman ratio 60%. As a figure, the contours consist of 3 colors with different severely level from the lowest to highest, is green to red. The LPR results indicate that generally fall in the center, CCP, and the south unit 6 portion, as well as the northeastern boundary of unit 5. From this result, we can estimate the unsupported length of pile DL per individual piles. The project schedule for unit 5 and 6 and CCP will be safe from the buckling instability with the calculated IP blue zone to greater than 2, and average IP is 7 for all pile, and the area indicate very low buckling index. If we turn to numerical simulation, all simulation will develop and execute using the OpenSys. To compare the hand calculation technique using the deterministic approach, we using the numerical simulation. The base acceleration embedded at the 20-meter depth adopted from the PNGA West during the 2007 Nikata Suetsuoki to investigate the effect various influence factor. We consider the behavior of soil in the adjacent near field and free field. This figure is the finite element mesh. The study considered the behavior of soil in the adjacent near and free field. This is the soil parameter input can be shown in the slide. There are 3 soil layers with the different soil parameters. This table shows the reinforced concrete pile with various concrete diameters 0.6, 0.8, and 1 meter. The numerical simulation performed with the different scenario, including the axial load, ground inclination, pile spacing, and diameter. The left side is scenario in the adjacent and near field conditions. The right side is scenario in the free field condition. The simulation result of influence of axial load, response of axial pressure at the stress bed of soil with the different axial load, and cast level ground, pile spacing 1.8 and pile diameter 0.6 at the depth 3 and 10 meter for the sand and clay respectively in the near field. The axial pressure will generally tends to increase with an increase in axial load. The clay acts as an impermeable layer against the dissipation of axial pressure. The increase in axial load will generally increase the effective confinement. The sandy soil will be liquefied and so shear resistance reduced 0. The simulation result influence of ground inclination, the response of axial pressure and stress bed of soil with the different ground inclination, the cast axial load of 1500, pile spacing 1.8, pile diameter 0.6 at the depths of 3 and 10 meters for the sand and clay respectively in the near field. The increase in the ground inclination generally would increase the axial pressure. The stress bed oscillates for the clay without the significant decrease in effective stress. The simulation result of the effect of pile spacing, response of axial pressure and stress bed of soil with the different pile spacing, and the case of axial load 1500, level ground and pile diameter 0.6 at the depths of 3 and 10 meters for the sand and clay respectively in the near field. The increase in pile spacing will generally increase axial pressure. The axial pressure slightly reduced after the peak value. The stress bed moved to reach to 0 effective confinement due to the increase in the pressure and indicates liquefaction in the sands. The simulation result of the effect of pile diameter, the response of axial pressure and stress bed of the soil, different pile diameter, and the case of axial loading 1500, level ground and pile spacing 1.8 at the depths of 3 and 10 meters for the sand and clay respectively in the near field. The presence of bigger pile diameter would generally appear a less drop in the axial pressure. The loss of sand exhibits 0 effective confinement in the last cycle, implying the triggering of liquefaction. The increased pile diameter would reduce of effective confinement in soil during the seismic motion. To compare results between the deterministic and numerical simulation, in numerical simulation we compute the maximum bending moment with the various influence factor versus the ultimate bending moment with different pile diameter and axial loading. The deterministic approach provides assessment buckling of pile with the IP is the HC over the DL. After we know the result, we can determine the buckling of pile in the liquefiable ground in the both deterministic and numerical simulation approaches. We use the interaction diagram moment and axial load from the project piles. Thus, we obtain the compute the maximum bending moment from the numerical simulation for absolute. The positive value is the maximum bending moment only occurring the positive profiles. Finally, we can compute the bending assessment of pile liquefaction ground using the deterministic and numerical simulation. The numerical simulation indicates the compute bending moment is less than ultimate the bending moment. So the two approaches will be safe from the failure of buckling of piles. In the final part of presentation, I would like to summarize the conclusion as follows. Liquefaction analysis indicating The foundation soil are prone to liquefaction due to the descent earthquake, showing the LPI greater than 5. Buckling assessment indicating the foundation pile will be safe from the buckling failure. Buckling index is greater than 2. Influence of axial load. An increase in axial loading would generally increase the axial pressure that would not magnify in the bending moment and would slightly reduce the spectral acceleration and increase predominant period of soil during the seismic loading. Influence of ground inclination. The higher ground inclination will increase the spectral acceleration and axial pressure and increase the maximum lateral displacement and bending moment. Effect of pile spacing. In increased pile spacing would generally reduce the response acceleration and axial pressure in soil and increase the maximum lateral displacement and bending moment. The effect of pile diameter. An increase in diameter of pile would increase the acceleration and response spectra in the soil and increase the maximum bending moment of the pile. Comparison of buckling assessment result. This study will be safe from the buckling failure with the compute bending moment IP is greater than 1. The compute bending moment is less than ultimate the bending moment of the pile descent. Well, that's my presentation today. Thank you for your attention. Have a nice day. Thank you.